Hi. In this video, I want to talk about electric potential. What is it? How is it different from electric potential difference and electric potential energy? Let's get started. And we're going to get started like we have done in the past with an analogy to gravity. So take a second. Which mass has the most gravitational potential energy, A, B, or C? I hope you see that it's C. Gravitational potential energy is mgh. So the greatest height will have the greatest potential energy. What about this one? Which location has the greatest gravitational potential energy, A, B, or C? I hope you're scratching your head. The question doesn't really make sense. Part of you might want to say, oh, it's still C because it has sort of the most potential energy if a mass was there. But what if you have a big mass at a lower height and a small mass at a higher height? You're running into that issue of gravitational potential energy depending on what mass you put at that location. So it's similar to electric fields in that you can't describe a location with gravitational potential energy because it depends on the mass you put there. So what do you do if you want to describe a location? Well, we can divide out the mass essentially. So take the gravitational potential energy per unit mass, mgh over m. M's drop out, and really what I'm looking at is just the gravitational field strength times the height. So what is that equation doing really? It's saying, hey, forget the masses. Let's just look at the location. And let's just say my floor right here is my y equals 0. Then relative to that, let's say this book was 1 meter above, then I would be at roughly 10 joules per kilogram. And then this book over here would be roughly 20 joules per kilogram. 10 times 1, 10 times 2. And what is that doing? It's saying this location, for every kilogram of mass that I would put here, I would get 10 joules of energy. 2 kilograms of mass, 20 joules of energy. 10 kilograms of mass at this location, and I get 100 joules of energy. But it's not really just describing that location, it's actually describing this entire height, because everything at this height, I would get the same number. Here's an important point about gravitational potential energy per unit mass. Does it depend on y equals 0? Yes, it does. If I choose my middle height as y equals 0, then that'll be the 0 joules per kilogram mark. But I hope you see that the differences will be the same. And this is exactly analogous to gravitational potential energy. When I had a mass at a certain height, what really mattered was the change in height, not whether I called this 1 meter or 10 meters, but it was the change in height between two different snapshots. So it's analogous over here with potential energy per unit mass. The potential energy per unit mass at any one location might change, but the difference between locations, that is going to be independent of where I choose y equals 0. So how does this relate to like electrostatics? I hope you can see that with the gravitational field lines in there, they're constant and downwards everywhere. And that might remind you of an example in our previous worksheet where we had two parallel plates and the electric field was like that. And there were these lines. If I had a charge over here or a charge over here, it would have the same potential energy. And really, let me just flip this around. It's exactly analogous, except instead of joules per kilogram describing a location, we're working with joules per coulomb. If I put a coulomb of charge over here, it would have, let's say, 0 joules of energy, whereas over here it would have 10 joules of energy. It's a number that describes the location and the energy a charge would have if it was there. There is an important difference, though, between gravity and electric, between the gravity and the electric analog. So this question might help you think about it. Which location has the higher electric potential energy per unit charge, I or F? Take a second. I hope you're scratching your head because it depends. Is it a positive charge there or is it a negative charge? If it was a positive, then I has the area of higher electric potential energy per unit charge. Because if I put a positive charge here, it would have a greater distance to accelerate over. By the time a positive test charge was pushed out to F, it would have some kinetic energy, and then would have the entire distance that a positive test charge at F would accelerate over, this infinite distance. But if I was to put a negative test charge over here, it would be able to accelerate over this distance. I'd get a certain amount of kinetic energy out. Whereas if I put a negative test charge a little bit further out, I would have a greater distance to accelerate over. And it would have a greater final kinetic energy. Just remember that the kinetic energy associated with the energy that you would get out of it, essentially, is what you should think of as the potential energy in that arrangement. So what do? This is an area of high potential energy for positive. This is an area of high potential energy for negative. It's similar to what we did with electric fields. We just say, forget about negative charges. Let's look at just what a positive test charge would experience. So because this area would have higher potential energy per unit charge, it would have higher electric potential energy at I versus at F, we say that this is an area of high electric potential energy per unit charge. We just forget about the negatives. In summary, I hope you realize I'm running out of breath just saying electric potential energy per unit charge. We shorten it to just electric potential. Key idea is it describes the location. The units are joules per coulomb, and it's relative to what a positive test charge would experience. Another key idea is that the reference point will affect the electric potential at a location, but the difference in two locations, that will be independent of the reference point. And so electric potential difference, we give the symbol V. Again, it's the same units, joules per coulomb. That's the important thing. It is different than electric potential energy in the sense that electric potential describes a location. Electric potential energy describes the energy a charge actually has. It's similar to the difference between field and force. In order for there to be a force, you actually need an object in that space. But if it's just empty space, then I can describe it with the field idea. Similarly, if I actually have an object here, it can actually have an electric potential energy. But if there is no object here and I just want to describe the location, I use this concept of electric potential, or joules per coulomb. That's the key idea. Hope that was helpful. Try the practice to deepen your understanding of this concept. Thanks for watching.